Okay, guys, let's see. There is a question here. There is one question: why it's important not to create group? As I mentioned before, group is powerful tool for CAD, but for when you go to grouping for truss structure, it's going to create problem in terms of the joint. Okay, the length is going to be changed. Then please do not create the group. But it's a good one for CAD when you want to create a shop drawing for those weldment and cut lists. All right, let's see. I'm going to start a new topic, which is chapter 5. Chapter 5, it's not in your midterm exam, then don't worry about the midterm exam. Chapter 5, from material that I'm going to cover from right now, is it will be part of final exam. Okay, and new material that we are going to cover from today won't be in your midterm exam. Let me start recording that one, and please turn off your mute yourself on your side, because I'm not going to answer any question during the lecture, but I'm going to give you time, maybe 5 minutes at the end if you have any question. All right.
This meeting is being recorded.
All right, let me just share the screen. There you go. Chapter 5. In chapter 5, what we are going to do, we are going to look at the different structure, which is frame analysis and beam analysis. You may say that we had beam analysis in chapter 4. You're right. Chapter 4, we had one-dimensional beam analysis, which is meaning that you are going to have only one type of loading applied to your beam, say tensile force, compressive force, or just the torque, not the combination of those. And that's why we said one-dimensional beam. Also, in this chapter, we are going to look at the frame analysis when we have more than one beam and they are connected in a different orientation, like frame that we have for machines. In machinery environment, we have lots of those frames. When it goes to a structural design, supporting system for heavy equipment, for example, you have lots of those frame that this is 2D and 3D, and we are going to deal with FEA with those structure as well. Comparing to chapter 4, chapter 5 from one perspective is easier because you are familiar with direct stiffness method, you are familiar with SolidWorks simulation and application in terms of weldment and 3D sketch. From that perspective, it's easier and you easily can go through the material. But on the other side, when it goes to beam, then in general you have more degrees of freedom. Then maybe direct stiffness method is in more heavy in terms of competition, in terms of the MATLAB and coding. But before talking about more detail, let's look at the beam theory quickly. In the beam theory, this is what we have. If there is a distributed load applied to a beam, as you see here, and say we have omega representing the distributed load, and it's a function of x, which is that distributed load can be function of x, and x represents the distance from the start of the beam. Then what's going to happen is if you have distributed load, that distributed load is going to create a slope, which is, we call it phi, and also is going to create deflection, which is why we call it y. Then we have two types of displacement here. We have a slope, which is a rotation, and we have displacement y. And you're familiar with the beam theory in your strength of material course. Then remember, you draw the beam diagram, and then you are going to draw the deflection, and also going to draw the slope. This is exactly what I'm referring to here. That this is just a quick review from what you had before. However, that function, y E, you can write the equation starting from the beam theory, which is called Euler-Bernoulli equation. That's a governing equation. You have EI, if the cross section is constant, EI, the fourth differentiation of y with respect to x equals omega. dy4 dx4 times EI equals omega. You had this equation before in a different format, different shape. Now, if you look at here, I'm going to draw a beam, as you see here, and I'm going to say, if that's a beam, and I'm looking at just one element, then there are two nodes, node number 1, node number 2. I'm going to say the length of this element is L. Displacement, in general, at node number 1, I call that one Y1, and E superscript represents element. Y1 and Y2 at node 2. We have phi1, which is the slope at node 1, phi2, slope at node 2. We have nodal force, which is F1 at node 1, F2 at node 2. And we have bending moment. When you're talking about beam, we have force and we have bending moment always. Not always, in general. Then we have M1 representing bending moment applied to this beam at node 1, and M2 represents bending moment applied to this node at point 2. All right, and now if you look at here, we say one should note that the positive direction of the moment at node 1 and the positive direction of the force at node 2 are opposite to the one used in the Euler-Bernoulli equations. We are going to consider those as a positive. Assuming EI is constant, what does it mean? It means that the material is constant, the cross-section is constant. For example, assume that you have I beam from 1 to 2. Material is fixed, cross-section is fixed. Then you can say that in this case, on the right side, you can take this EI out of this differential and bring it out, and assume that there is no distributed load. Then that would be 0. Then that would be your governing equation. Now, we are going to say, if we apply boundary condition to each point, here you have the force, moment, slope, y1, you have force, moment, slope, y2. If you apply that boundary condition and solve this equation, which is the proof is here, but I'm not going to talk about the details. If you are interested, please go ahead and read those and ask me if you have any question. Then you will end up with the relationship between the forces, and finally the relationship between the forces and the displacement can be simplified as you see here. This is exactly the same as what we had before. In this case, we have F equals K times D. However, this is for element, meaning that that matrix, which is 1, 2, 3, 4, 1, 2, 3, 4, 4 by 4 times EI divided by L cubed, that the whole parameters that you have is a scalar multiplied to this matrix. That represents element stiffness matrix for beam this time. And I simplified that one here. See, this term is here, and I call that one beam element stiffness matrix. But this is just for one element. And in this element, we have node 1 and node 2. Let's see what's going on in terms of loading. In terms of loading, we have AF1 plus RF1, applied force at node 1 plus reaction force at node 1. Also, this is the first time we have moment, and apply moment at node 1 plus reaction moment at node 1. Same goes for nodes 2. In terms of displacement, what we have 2 degrees of freedom here. We have 2 types of displacement here. We have y and you have phi. Y1 and phi1 represents displacement and the slope at node 1, and same goes with y2, f2. The reason your element stiffness matrix is 4 by 4 is, and we have for one element, see, one element, we have 2 nodes, and at each node we have 2 degrees of freedom. One is rotation and one is displacement. Then 2 nodes times 2 degrees of freedom, then you will end up with 4 by 4 matrix. And that represents element stiffness matrix for beam, but 2D planar beam. We are not talking about 3D element yet for beam. And if you want to solve this problem, most of the time what you have more than one beam. You have beam segment connected together, and you may end up with different element stiffness metrics. For example, if you look at here, this element stiffness matrix, you may end up with L1 and E1. Even it doesn't have to be one material, even can be different material, and L, this is the length of the element. Then if you have, say, let me just draw something here quickly, then it's clear. See, in this one, we had one beam, 1 and 2. What about if I have another segment? What about if I have another segment here? This is element number 1, this is element number 2, this is element number 3. Now, for here, I have K1E, for here I have K2E, and here I have K3. Those are element stiffness metrics, and for each one I have L1, E1, and what was it? I1. Again, E2, L2, and I2, and so on. Then for each of those, you're going to calculate, element stiffness metrics. Now, if you are looking at the whole structure, which is the beam, for example, in this case, 3 segment, then you need to end up with assembly of those elements. We are going to do that using the directed stiffness method. And if we say capital K represents the summation of all of those K elements, and capital F representing the summation of those elements, forces, nodal forces, and D represents the summation of those displacement. If you put them together based on directed stiffness method approach that we said, you will end up with global force vector, global displacement vector, and global stiffness matrix. And this is more or less same as what we had so far. Then if you find those, you can create the equation, say F equals K times E. Then what's happening here is that in that equation, F represents loads represented at global coordinate system. K represents the stiffness matrix represented in global coordinate system, and D represents the displacement expressed in global coordinate system. Then everything will be represented in global coordinate system. And same as before, you are going to use MATLAB and solve the problem for unknowns that you have in your specific problem. Now, one thing that I want to make sure here is about the beam is the components of stress, because you should be able to interpret the result when it goes to SolidWorks simulation later on, also in direct stiffness method. So far, what we had, say for truss structure, the truss member is a two-force member, meaning that the truss member is either in compression or in tension. Then you have either sigma positive, or you have sigma negative, which is normal stress. We had torque, one-dimensional. We had torque for one-dimensional beam. If you have torque, it means that all you have is a twist, which is you have just torsion. But when it goes to the beam, you should be able to identify the component of stress, because now we have, you are familiar with the concept of combined stress. If you look at here, for 2D planar beam, I can have shear, I can have axial, and I can have bending moment. Then if you have three components at each cross section, then F axial, which is the normal force, is going to create a sigma, which is the nature is normal stress, and the magnitude is constant, which F divided by A. If F is constant and A is constant, F divided by A is constant. Then as you see here, that component of the stress coming from normal force is a constant, and that's the way you can calculate the axial. When you have transverse shear or you have shear force, if you back to the strength of material course, sigma shear, which typically we call it tau, is the distribution is based on equation that we have, which is I think IQ divided by IT, something like that in the textbook. If you look at that one, the distribution is not linear, is not constant. It means that the shear at the outer layer is 0, at the center of area or neutral layer is maximum. This is that part. And also, if there is a bending moment, we know that bending moment is going to be 0. The sigma generated by this bending moment would be 0 at neutral axis or our neutral layer, and would be the magnitude, the maximum would be the outer layer, which is equals MC divided by I. Now, that's a quick review from the stress component in a beam. You are familiar with those from your strength of material course. What I want to make sure that here is later on, when you want to do measurement, especially when it goes to SolidWorks simulation, you should be able to interpret. If you say, I want to see normal stress, what does it mean? It means that you are going to look at the combination of normal stress here and normal stress here, because these two are same nature. If you're looking at one misses stress, then you are going to look at the combination of all those three stresses. Hopefully that is clear. One more subject that we need to consider here is what is called equivalent nodal forces moment. Let's make sure that in the beginning you are not going to get lost quickly. What I'm talking now is about direct stiffness method. Whenever you want to use direct stiffness method, you need to move the forces to the node. All right, move the forces to the node, because direct stiffness method is based on nodal forces and nodal moment. Let me just back here and show you something. See, remember this equation? We developed this equation, this element stiffness matrix, based on this free body diagram. In this free body diagram, we said we have nodal forces, as you see, applied to the node. Between, we didn't apply anything in terms of the loading. And based on this assumption, what we did, we developed that element stiffness matrix. All right. However, as you know, in some cases, that's not the case in terms of the loading. If you look at here, if I say this is one beam, one element, and I want to solve this problem, and I want to find the stress and use direct stiffness method. I look at this one and say, okay, how can I solve this problem? In this case, there's a distributed load applied to this beam, and there is no way that you can use the equation that we developed based on nodal forces only applied to the node. I hope you see the issue here. The equation that we developed for the element stiffness matrix is based on the fundamental assumption that you do not have any forces or torques or moment between the loads. In real application, if you want to use that element stiffness matrix equation, we see sometimes we have, for example, a constant or uniformly distributed load. Then now the question is, what should we do? One approach is to use equivalent nodal forces moment. The whole concept is this. I'm going to replace. Please pay attention to the concept here. I'm going to replace this distributed load to the node such that the result in terms of stress and deflection will be the same. One more time. I have this distributed load. I want to get rid of this distributed load. I cannot delete it, and this is a real life problem. I have that load. But what I'm going to do is I'm going to find what is called equivalent nodal forces and moment. I'm going to apply those nodal forces and moment to the nodes such that the result is same. In order to find the magnitude and the direction of those nodal forces and moment, you need to back to the beam theory. What I did in the textbook, you can see I prove how you can find for this particular load distribution, how you can find the magnitude of those nodal forces and moment. The proof is there if you are interested. Then a step-by-step approach, how you can reach to the point that instead of that beam, now I have this beam. The result is same deflection, same stress in the element. But the good thing now here is what you have here, those are nodal forces and nodal moment. Meaning that I can solve this problem and end up with the result that I have for that problem. And that's the power of equivalent nodal forces and moments. Now, what should we do? Should we every time go through those equations and find the nodal forces and moment? Is it something that should be some sort of a reference, some tables to go through those equations, solve the problem, find this, and then based on the loading, try to create a table. Then every time you don't have to really spend time to repeat this procedure. What I did, if you look at your textbook, in your textbook, what I did, I put some of those equations here. You can see them. See, for this case, for example, it's here. See, you have the proof for that one. If you are interested how we move from here to here, how you can find those nodal forces and moment in your textbook, you have the proof. You can do the same procedure for when you have your loading, like linear distributed load. Here is 0, other side is omega. Now, as you see here, the magnitude of F1 and F2 and M1 and F2 is going to be from here. Also, please pay attention to the direction. Direction is also important. Or if you have a simple force and you want to transfer that one to the node, that one was for distributed load, that one was for distributed load. What about if you have concentrated load? Same, what you have is just those equations. You have to, if you want to find why we have those equations, same procedure in terms of proving the proving this load case scenario. You can go with this load case scenario, and you end up with another set of equation. You have the equation in this textbook, and this is what we need for this course. However, for a variety of those loading and forces, you can go to the handbook, and there are references that you can find those nodal forces and equivalent nodal forces and moment. All right, this is what we have in terms of nodal forces and moment. Now, let me just go to one example to see what we are doing in terms of this approach. See, example 5.1, which is we are going to work on this one during the lab session this week. This is the beam. What you have fixed fixture at both ends, length 3 meter, 2 meter. I have counterclockwise bending moment here, which is 10 kilonewton meter. I have 5 kilonewton force applied to this point as well. Then what I have here is I have one concentrated load and one concentrated moment applied to this beam. In terms of information, we have E, material is given. We have I, cross-section is given. And we have beam AD by 6.6. If you need any information, you can find it from there. And what we are looking for, we are looking for displacement and rotation at the point of load application here. How much is the displacement and the slope at this point? And also, we are going to look at the reactions. I'm interested to find the reaction forces here. You cannot solve this problem because this is statically indeterminate. We cannot solve this problem using simple sigma fx equals 0, sigma fy equals 0, sigma moment is 0, based on the equilibrium equation that you learn in a static course. You can't. With direct stiffness method, we can not only find the displacement and the rotation, we can find forces at those nodes as well, including the reaction forces. Now, in order to do that, remember I said there is a stiffness matrix. I have two elements here. From 1 to 2 is one element, from 2 to 3 is one element. Why from 1 to 2 is one element? Because there is no change in terms of material, loading, and geometry. Then that part can be considered as a one element. Then you have from 2 to 3, you have the same. There is no change from 2 to 3. And then I can say this is one element. At this node, I'm going to apply those forces. Then I'm going to consider that one as a element number 2. And then I have node number 3. Then I have element number 1, element number 2. Then I need to develop two stiffness metrics for those elements. K1, which is, the equation is clear. I have to put L1, which is 3 meters, E is given, I is given, and just substitute those values here. And then let's see what is the size of global stiffness matrix here. We have 1, 2, 3. We have 3 nodes, each node 2 degrees of freedom. Then you will end up with 3 times 2, 6 by 6. Then I'm going to end up with expanded element stiffness matrix for element number 1. Then I'm going to create a same as before, 6 by 6, put all the zeros. However, here what's happening is you have D1, phi 1. Let me just put it here. You have D1, phi 1, D2, phi 2, and D3, phi 3. Same here. D1, phi 1, D2, phi 2, D3, phi 3. Now I'm going to see what is the element 1 connecting what nodes. Element 1 is connecting node number 1 to node number 2. Then this is node number 1 and 2 area, and this is node number 1 and 2 area. And this is the area that I'm going to put this matrix. We're going to continue. Same for element stiffness matrix. For element 2, I'm going to find the expanded element stiffness matrix, this time between 2 and 3. Then that would be the area, because this is the area I have 2 and 3. Here, this is the area that I'm going to have 2 and 3. And that would be the area. Global stiffness matrix, just put them together, sum them up. Then that would be your global stiffness matrix. Now I'm going to write down the equation, F equals K times D. And as I said, D is Y1, phi 1, Y2, phi 2, Y3, phi 3. On the other side, we have applied force plus reaction force, applied moment plus reaction moment for all 3 nodes. And that would be the equation. Now you need to substitute boundary condition. Let's look at the boundary condition for displacement first. For displacement, since this is fixture, see, get back here and show. See, there is no rotation, there is no displacement here. There is no rotation, no displacement, because those are fixed. Then D1, as you see, Y and phi for node number 1 is 0, Y and phi for node number 3 is 0. That's the boundary condition that I'm going to apply. Let's see what's happening here in terms of applied forces, reaction forces. This is area that some students make a mistake. If you look at node number 1, let me just draw it here. I'm not going to draw the rest, but here is what's happening. This is node number 1. This is the support. This is the fixture. Then if you look at here, there is no applied force and applied moment. See, there is no applied force and applied moment. Then what you have here is you have 0, 0 for both applied force and applied moment. However, at this node, we have both reaction force and reaction moment, which this is unknown. We don't know it. This is the first thing. Oops. For node number 2, let's see what's happening for node number 2. For node number 2, which was in the middle, now we have 55K and I think what 100 kilonewton per meter, something like that. Let me just double check the number. 10 kilonewton meter, sorry. That's a 10 kilonewton meter. Then at this node, I do not have, here's the point, that I do not have any reaction. Then reaction moment and reaction force is 0 for node number 2. However, I have 5K and 10K, 10 kilonewton meter for applied one. And same goes with the third one. Now, the rest is straightforward. What you have here is you have, how many unknowns you have? 1, 2, 3, 4, 5, 6. You have 6 unknowns and you have 6 by 6 metrics. It means that 6 equations. All you need to do is write the code and solve the problem. The good thing here is you can find both displacement and the reaction at node 2. Also, you can find reaction forces, reaction moment at node 1 and 3. That is one way to solve a statically indeterminate problem like this one. Remember in the beginning, I said you cannot solve this one because it's a statically indeterminate problem. Now, using direct stiffness method, which is finite element analysis, one approach in finite element analysis, you can solve those kinds of problems even that you couldn't solve with traditional equilibrium equation. And let me just move on one more time. Just make sure that we covered everything. Now, and you can solve this one. Then this area from here, you don't have to follow that one because you are going to use math. So I simplified for that one in case. But here is the code that you are going to write in order to solve this problem. Again, you have some things. This is the variable. You are going to define the section property like I and the material property here. Just be careful, material should be MPa, not gigapascal. I convert that one, see? And then you are going to end up with a stiffness matrix here. All right, you're going to end up with element of stiffness matrix here. You're going to substitute to find K1 and K2. You are going to sum them up. You're going to substitute boundary condition, and you're going to write the equation and solve the equation. See, the pattern is exactly the same as what you had in chapter 4, but definitely the equation is different. And we're going to practice this example 5.1 in our lab session this week. Let me stop sharing and
The recording has stopped.
stop recording. All right, any question about material that I covered today? Again, we have time this week to go through this example during the lab session, but any question right now? Is the reason that you use the subs command instead of defining known variables? Because I want to put subs. Because if you put subs, it means that every time you want to change, you're going to change the values in a one line instead of following the code and find that number. If you define a variable, just substitute the variable. Any other question? Yes.
I just had a question about the Wellman groups. I was wondering, was there an alternative to that?
What do you mean alternative? What do you mean?
I think you mentioned that it's not good to use the groups. So I was wondering.
Yeah, Nikita, be careful about what I said. I said for CAD, when you want to create a group, is as a matter of fact is a powerful tool and use it for CAD, not this course. You can end up with a cut list. When you go to bill of materials, you have all the information that you need. For this course, please do not use group. There is alternative. I talked about alternative maybe 2 years ago, and what the result was disaster because the student didn't get the point, or not all the students, some students, and they mix up in the midterm exam. They said, oh, we tried the alternative, we didn't know. I said, okay, you know what? Forget about it. This is the CAD issue. If you are interested, we can talk about it separately. Yeah. But let's assume that there is alternative. Back to your question, but I'm not going to talk about alternative in this course because it's just a CAD issue. Don't mess up with CAD. Focus on the core of this course, which is finite element analysis.
Okay, thank you.
You're welcome. Yeah. If there is no question, okay, then I'm going to talk to Olivier first. See that what is this change? Because I assume that machine design is on 28, 2 weeks ago when I got email from Olivier. And that's why I said, okay, second is the best for us. That's the last one I can make the exam. Otherwise it will be a horrible situation. Let's see, let me talk to Olivier and see what is the issue. But I'll keep you posted on this issue. Still we have 2 weeks to go. Have a good one and see you on Wednesday.